Hello. This is it's kind of a weird again, just like a few of the other the Unit 2 physics videos. This particular one is obviously for D1. I'm not gonna, for those of you that have watched that so-called interesting FP1 video where I thought it was a D1 video, FP1. I don't know, whatever. As I say, in this video, I've just begun with a few points I think. And not such a topic on its own, although I probably could have included them when I was talking about the types of graphs, you know, the Eulerian, non-Eulerian, bipartite, etc, etc. Could have mentioned it in then, but I'm just doing it to make sure that I've definitely included it somewhere in my channel, okay? So, specifically, let's just hypothesize a graph here. So we've just got a few points. Standard graph, okay. Sorry, 1 second. So we've got a graph, and we've got arcs, we've got nodes. It's a complete graph, okay. Sorry. Let's call this vertex A, B, C, D, and E. Okay. Now I'm not going to put any. I'm not going to complete it any more than that because I'm not really wanting to do any questions that involve that, okay? So, let's just think for a second. A couple of questions you could get asked. If we are told, okay, so actually one thing that, yeah, I'll just bring it up. The equation is this equation, okay, Serrian equation, is the sum of all the orders, and I'll explain about that in a minute. All the orders is equal, over over 2 is equal to the number of arcs. Okay, so what do we mean by that? Sum of all the orders? Well, an order of a node, okay, is the number of lines that are going into and from it, okay? So the order of B is 2, 1, 2. The order of A is 2. The order of C is 3, the order of D is 3, and the order of E is 2. Okay? So, let's just add all them up. So it's 2 plus 2, 2, 4, 3, 5, 8, 10. Okay, so there's 10 orders in total. So you do that over 2, you get the number of arcs. So there should be 5 arcs here. 1, 2, 3, 4, 5. Oh great, I've done something wrong. How the hell have I got that wrong? I don't know. Basic adding skills, and that's that's not very good, is it? But anyway, that holds true for. I tried to prove it to you, and obviously my counting skills let me up. But you get the idea. Okay, so there should be 10. It should be. We should add up all the orders, divide it by 2, you should get the number of arcs. This leads us to a couple of points, okay, because obviously this number of arcs has to be an integer. In other words, it has to be a whole number. So therefore, the sum of all the orders must be even, okay, to have a proper graph. If we have, so therefore, this allows us to say a few things. Which kind of relate to the Chinese postman algorithm, that kind of section of the graph, of the topic in D1. If you add, now this is where the wording gets stupid. If you add an even number of odd nodes, they will cancel out. It's just like the same as thinking, if you times two negatives, if you times an even number of negatives together, you'll get an even number, because the negatives will cancel out with each other. However, if you times together an odd number of odd, in other words, a negative number, an odd amount of negative numbers, okay, together you'll get a negative number. So you apply that kind of theory to adding them, works the same. So if you get, that's not a brilliant example actually. Anyway, so if you add an even number of odd numbers, you'll get an even number. But if you add an odd number of odd numbers, you'll get an odd number. Okay, so let's just do an example of this, if this even works. So let's say we're going to add 2 plus 2 plus 4 plus, and then we'll choose 2 odd numbers, So 9 and 9 and 11. Okay. So if we add that, it should be even. Okay. And obviously in that case it is. So it's 2 plus 2, 4, 8, 17, 28. Okay. And that comes to an even number. I was worrying that they would. Okay. But if we added another odd number onto that, say 9, okay, that would come to 27, in which case it would be odd. Okay, so hopefully you can see, but you know, it's just a basic principle of maths, that. Okay, so therefore we need an even number of odd nodes. Okay, so if it asks why that is the case, and generally in a Chinese Postman algorithm it will be the case, that's because you need to pair them up. Okay, and if you have, that's another way of looking at it, if you have an odd number of odd nodes, okay, because in the Chinese Postman algorithm you'll do pair 1, okay, you'll have a certain number and you'll need to pair them up, so H and E and C and D, for example. If A was also an odd node, okay, just say, I mean these aren't, but just say it is, then you wouldn't be able to pair A with something that hasn't already been paired. Okay, now obviously you would go with different pairs, pair H and D together and C and E, but the principle is we can't have an odd number of odd nodes, because then this would be odd, and then when you divide it by 2 it would result in a decimal number of arcs. Okay, and obviously you can't have that. And you can't say, oh, we'll round it up. Well, you can't, okay, because you can't just involve an arc that wasn't there and change this equation. Okay, so that's one of the first things I want to mention. A tree, yeah, so a tree is basically is a graph where all the nodes you can't get from. I'll draw a tree and then I'll probably better drawing it. Okay, so say we've got a single point here. Looks something like this. So remember, a tree is where you can't get to every single node without at least transversing one path. In other words, you can't go from here to there and then to there without transversing this path again. Okay? And one of the principles surrounding a tree, okay, is you will always have n minus 1 arcs. And you go, well, what is n then? Okay? Okay, n is the number of nodes. Okay, so 1, 2, 3, 4, 5, 6. So therefore it should have 5 arcs. 1, 2, 3, 4, 5. That actually worked. So therefore, hopefully that proves it to you. But that's something you should know for trees. It has n minus 1 arcs, where n is the number of nodes. Okay, it's the number of dotty things. Alright, the next point that I want to make. It might give you a given graph and say, how many times will you visit node E, or whatever it might say. Okay? And in that case, so say we've got, this is just a single point of the graph, okay? So this is a single node, and I'm not going to draw the whole graph, okay? So, it may ask how many times you're going to visit node E. You add the order, you work out the order of that node. In other words, a line's coming into and away from it. That's 1, 2, 3, 4. Therefore, you will visit node E twice. Okay? So in other words, to find how many times you visit a given point on the graph, you work out its order, remember the number of lines coming in and away from it, over 2. And that will give you the how many times you visit that particular node. Alright? Yeah. By the way, in the Chinese Postman algorithm, okay, when you've worked, say we've got these pairs, I'll just I'll just come up with a couple just to show you this given point. Okay, so we'll go pair 1, pair 2. Okay, so say we have these 4 odd nodes in a given graph, A, E, F and G. Okay, pair 3. Okay, say you would pair A and E first, then F and G, and A and F and E and G, and then you would finally pair A and G and E and F. Okay, so obviously I'm not going to come up with a graph and explain it to you, but let's just hypothesize something. That the first pair came to 90, the second pair came to 80, and the third pair came to 70. Now obviously, in a basic, let's say as well the total weight of the graph was 1000. Okay, so 1,000 kilometers, 1,000 meters, doesn't matter. This is the total weighting of the graph, okay? And obviously in a Chinese Postman algorithm, sorry, I just wanted to have a quick look at something. Okay, so obviously with the Chinese Postman algorithm, if this was the case, okay, ask you now to work out the shortest possible route, alright, you would, let's say the length of the shortest route, given, including the ones that have to be traversed, it would be 70 plus 100. Now, if it asked you to state that route, okay, you'd have to state the route you took from A to G and the route you took from E to F, alright? Now, one sec, just get rid of that, so that was A to G and E to F. Okay, so there's one more question actually, and it came up in January 2011, okay, it was question number 5. I'm just going to go through a similar example. Okay, in that particular one, it said that the machine must be delivered to a point D, okay, and it can only start, so basically it must be delivered to one point, okay, but it may, basically, generally with these Chinese Postman algorithms, it will be resurfacing, or someone has to walk over a certain distance and needs to go over each road twice, okay. So it says a given machine will have to be dropped off at one of these odd nodes. Say, for example, it might have to be dropped off at A, okay, but it can finish at any vertex. So basically, if we applied it to this, actually, let's just put some numbers to this. One sec. So be 45, 45. Oh, as you know, that's a bad idea. One sec. Do that as 40, 50. Sorry, one sec. I'll just put some numbers to this, and then I can explain it better. And then that'll be 20 and 60, and this can be 31. Can be 30, 40. Okay. No, I've actually, one sec. Sorry. 16, 10, 65, 5. Okay, so these are just some hypothetical numbers. I said from A to E it's 40, from F to G it's 50, from A to F it's 20, from E to G it's 60, from A to G it's 65, and E to I is 5. Now, as I said, this is a completely hypothetical graph, assuming we've worked it out in the quickest possible way for each one. Okay? And it might say the machine has to be dropped off at point E, okay? So in other words, it has to start from point E but can finish at any vertex. In other words, any node. In other words, we have to select the node that starts at E, okay, but it doesn't matter which one we pick that ends with, okay, so it can either be A to E, A to F, or A to G. Okay, so in that case it says, it might say, and it may finish at any vertex, as I said, each road must still be traversed at least once. Given that the route is to be minimised, obviously pick the shortest route, determine where the machine should finish. Give your reasons to justify your answer. So that's kind of January 2011 adapted to this particular example. Okay, so I have to go through the example for January 2011. Okay, so for that particular example, you should look for the smallest pair. Okay. Sorry, one second. Sorry, one second. I just need to go over something again in my head. Yeah. Right. Okay. See, just trying to get it in my head in a way so I can word it properly to you. Okay. So as I say, following that question, what we have to do is pick the smallest pair. That. Okay. So if we look for the smallest pair that does not include A, all right. The smallest pair that does not include A is E to I, okay, which is 5, alright? The smallest pair that does not include A is E to I, which is 5. So therefore you'd say it should finish at G, okay, making E to I even. So that'd be the answer to that question. So just to go over it, okay, if it asks you to minimise a route but says it must start at any point but can finish at any other point, okay, you look for So if it says it must be delivered to a given node, okay, to start at, so it must start at a given point, say A, you look for the smallest pair that does not include A, okay, and then the one that is in this, okay, in whichever pair it is in, okay, so in this one eta is in pair 3, okay, you look for what A is connected to in that pair, okay, and say therefore it must finish there, right? Because obviously if you've got two odd nodes in a given graph, okay, you start drawing it at one of the odd nodes, you will finish, no matter how you do it, at the other odd node, as long as you don't go back over yourself. Alright, so that's the answer to that question. I really think that's quite a challenging one, but it was worth 3 marks, only worth 3. So hopefully that clears that up. If it does, but as I say, when I do the Jan 2011 paper, it will be a lot clearer than that, I think. Alright, as I say, that was just an example I came up with, just a hypothetical graph, so you probably won't get such disparity as 65 and 5. Although you could do, but just an example. Alright, so thanks for watching, and we'll see you in the next video.